Now things will get a little more interesting here. So what we have seen so far in this series, if you have checked the previous two sections of the series, that if you are having a connection like this first graph, where traveling from one node to another is you do not have to pay extra cost, right? It's like equal from going A to E, same as from E to D, for example. If these are the given conditions, in that case, if you have to find the shortest distance from a given source to every other connected city, every other connected node, or to a given destination, just for example, if C is your destination. So if there is no wait, if there is no extra cost of traveling via any edge, then breadth first search is good enough for us to find the shortest distance or the best distance. If we are calling shortest is best, then that is the best distance. That we have seen in the first section. Then we learned in the next section that if for similar connectivity, if we have that for every route there is a cost involved with it, which is a real world scenario, right? That if you go from A to C directly, then maybe your flight is some $1,000. Okay, but if you go from A to D, it might be a cheaper flight, say $20, because of too much, very frequent flights or whatever, right? And from D to C, if you go, then it might be another, you can say, $70 because of, again, some connectivity that this route is very frequent, blah, blah, blah. So here, basically we apply Dijkstra, which like we have seen that it's nothing but BFS, breadth first search only, but using priority queue in place of queue in breadth first search. Yeah, why breadth first search will not work? Because if I would have done breadth first search, then from A to C, I will directly close it in, that 1,000 is my cost and this is already visited. Hence, I cannot revisit it. But if I'm applying Dijkstra, then I will not pop C from the queue until I find the best route. So that we have seen, no need to discuss it here in detail. In previous section, we have done it already. Now, if things get a little bit more complicated, by means near real world scenario, which is a twisted scenario, think of that similar connectivity, that my source is city A and I need to reach to every other city, you can also say, or I have to reach to C is my destination. Okay. Now, let's suppose the flight from A to C is direct. Again, same $1,000. A to D is 20 and 70. Even if I'm using a priority queue now, maybe this I'll be able to close via D and C. Now, special cases, think of that if you go A to E, which is, let's suppose, $30. Okay. But if you go E to C, assume there is something extra you will be able to do. For example, we always hear this example that if you buy an iPhone in India versus if you go to Dubai and buy an iPhone, then you will be able to travel plus buy an iPhone, come back, and that will be the cheaper deal or the better deal because of taxes or whatever, right? So assume that from E to C, somehow, even after paying the cost, you will pay some -10. That will be the overall impact via going on that route. So here, for simplicity, we'll say the weightage of this route is -10. Now, in this case, if I would have done priority queue, I'll close E first, right, via 30, and then C, because C I will be able to close via D before E, because D is having only 20, then D will pop out and it will update C with some cost. But if E I will explore in the end, maybe by then C is already kind of concluded. Means if I just increase it from 30 to say $100, it's not 30 now, it's $100, and here I am doing minus $70. Okay, but from D to, if A to D I'll go in 20, D to C I'll go in 70, so overall cost to reach to C will be 90. E is already 100, so even if I would have pushed it into a priority queue first, I will not pop it out until C is already popped out, because C cost is already 90, which is lesser than 100. So C is already concluded. This city is already concluded that best cost to reach there is 90. But this is where in Dijkstra also, in a way, we are doing a greedy approach, that we are assuming the best cost to reach a city, if that is minimum, that will be the best route. But that's not the case here when negative weightage is involved. Because if we see, even though to till E we are paying a higher cost, if I will go via E to C, then ultimately cost can be improved by 100 minus 70, which will be $30. $30 should be the best answer, right? But Dijkstra cannot do it, and breadth first search definitely cannot do it. Like we saw, if there is a weightage in the edges, by breadth first search simply fail. So do not even need to think about it. Now, what works when negative weightage is allowed? And that real world scenario can be anything, like the one example I gave you. But in any given form, if negative weightage is is there on an edge, that is where one algorithm which comes in picture, and it is very easy once you learn it, is Bellman-Ford. This algorithm works, gives same result what Dijkstra gives, but even when negative weight is involved. And I also just communicated why with negative weight Dijkstra will not work, because that is a greedy approach where we would have traveled to a path thinking that this will be the best because of a given weightage on that, but we cannot imagine what will happen in future. And that is where Bellman-Ford will come in picture. So let's continue learning about this algorithm first. Okay. To establish the understanding of Bellman-Ford, there are two things which we need to notice, which is like very easy. Imagine you have total five nodes or 5 cities. Now, in a worst case scenario, if I have to go from A to D, worst case scenario, how many nodes or how many edges, how many routes I have to travel? I'm talking, ignore the cost involved on it, but how many? So worst case scenario, because there are total 5 nodes or 5 vertexes or 5 cities, whatever you want to call it, that means in between you have to go to every other node. So B somehow will be in the middle, C will be in the middle, E will be in the middle. Right now I do not even know what the connectivity is, means who is connected to whom. But this is the worst case scenario. If my source is A and if my destination is D, in this case, this is my worst case scenario. Now, what do we get from it? So if I just draw the routes, that from A to B I will go somehow, B to C I will go, C to E, E to D, right? In that case, how many routes we are supposed to travel? So 1, 2, 3, 4. Okay. How many cities we had? Total cities is 5. And this will be true in any graph, right? We are talking about the worst case scenario. Okay. That means with in a graph with number of vertices v, the total number of routes we have to travel from a source to a destination will equals to be v minus 1. That is the first thing we just need to establish. Okay, so total number of routes is equals to v minus 1. Got that? That's the first one. Now let's move on. Now we have seen that we need v minus 1. In worst case, v minus 1 routes from a source to a destination. Now let's imagine same that A is my source and D is my destination. In that case, from source to source, the total distance, what we know in the beginning is 0, that no cost involved, right? And rest everything, because we do not know, we'll imagine that we need infinite cost to reach there. This is normal, we do in most of the algorithms. Now, here we are focusing on the routes. Okay, so if we just check for every route means an edge. For every edge, what is the, if we can, better, you can say, how we can process an edge here. So this A to B, what it is telling me is A involved, B involved, and cost is 20. So what it can tell me that what is the cost to reach to B. If I just process this edge first, what I will get is that I know what is the cost involved to reach to A is 0, and this edge is having a 20. So for source, I know the distance. For destination, the distance will be whatever is to of the source, and then whatever is the edge weight we can add. So we can safely update the distance to reach to B is 20. This is not final cost, but this we are updating when we are processing this edge. So we will process every edge like this. What will happen is all the edges which are connected to my source, initiating from the source, those will be processed and update the neighbors. This is very similar to breadth first search, Dijkstra. Same thing is happening in Bellman right now, that you are updating how you can reach the neighbors in the cost which is involved to pay via that particular edge, the direct one, right? But for you can say, because A is almost connected to everything including D, you will be able to get something updated here in the first iteration itself, right? But like we said, we cannot say this is the best distance. This is just the greedy, or some of the nodes, if there is like another, you can say F here, which is not even connected to A, it is only connected to E, that will still have an infinity in the starting. That will be the cost, right? If we do the same thing next time, means I'm processing every edge. So first time I processed every edge. So let's say A and B I did, same way I'll do A and C. So when I'm doing A and C, which is having 20 as cost, it will update this to 20. It will similarly update my D to 700 as cost, and E to 100. That is the weight on the edge. F is still infinite. If that is another edge I'm adding, let's suppose I'll add 70 here. Okay, that is still infinite. So I processed all the edges once. Now, same thing, if I do one more time, what will happen? So far, I only, for this particular D destination, I only processed one, you can say, direct routes. That is why we are calling it one time processing happened. If I do it another time, that means next time. So what will happen is we kind of explored all the neighbors of source directly, but when I'm doing it second time, now it will also include that if there would have been one stop, this B, C, E, then how we will reach to D, will there be a better cost or not? That is what it is checking in the second time. Let's just do it again. So second time I'm processing for A to B, nothing will change because A is still 0 and there is a direct edge, so nothing will change, but we'll still process and we'll see if we can improve this. So when we will come to, in second process, when we will come to C to D, this edge, which is having a weight of 70, this particular edge, right? At this time, we will see cost to reach till C, we have updated to 20 in the last iteration. In this iteration, we know if we add 20 to the 70, the cost to reach to D should be 90, not more than that. Right now, D is having 700. Hence, just via one stop at C, the cost will be reduced to 90. So this we will update in our distance array. Okay, this is updated. Now, like I said one thing in last section, worst case scenario, we have to reach, we have to take how many routes to reach from source to destination. That was V minus 1. So what we need to do is same thing which we are doing here, that process every edge and see if I can better the distance. This, if we do V minus 1 time, that means we will be able to explore every path from source to destination, and that is where the whatever is the best answer, that will come here. It takes some time to analyze it, to understand this point, but that is where there are two important sections involved in this. First was that V minus 1 time. V minus 1 is my number of routes, and then for that many times I am processing every edge, which will give me the best cost to reach to that destination of that edge. Okay, what is happening here is I am kind of increasing, I'm kind of bettering the cost involving more edges in the route. Okay, like for D, I'm kind of expanding my exploration around D one by one. First, I just thought of how to reach C to D, right? In next iteration, how to reach to D from A. Okay, this is, we are seeing it in a reverse direction. Same we are doing in forward, that from A to C in how much, and from A to C to D, what will be the cost. So that is how my graph is expanding. And we will see that not just in case of negative edges, but there can be other use cases of this algorithm which can come in the interview, and which is not obvious to kind of think about that in the interview when you are if you are not in practice with this algorithm. All right, let's go over the code for this one. So Bellman-Ford code is going to be very easy once you know the concept, the basic concept of the algorithm. So let's try to write that code one by one. Okay, so I'm trying to define the standard function like we did for other algorithms as well. So first thing first is we will create a distance array, which is this. Here we were maintaining that by default everything is infinity and source is 0. Okay, so same array we'll try to create first. Now here, so what we are doing is we are taking one variable, I'm calling it infinity, just for clean code perspective, but we know what do we need to put in infinity. It's like maximum of integer. If we are working in whichever language we are working on, that can be language specific. So it's just that I'm taking a variable where I'm defining my infinity number, and then in every element of my distance array, which is of size n, in our cases it will be n means number of vertices, right? So for every element, the value is infinity by default. This is the way to do it in Python. In whatever language you are coding, you just need to put in every element an infinity first, and for source, whichever source is given, we just do 0, as by default you can say to reach from source to source the cost will be 0. Now moving on, then what we should do is, like I said, we will so we call it relaxing the edges, means we will process every edge, right? So how do we process every edge is number of vertices time. We are going to run this loop. Why? Because like we established here, that for any given route here from source to destination, worst case scenario, we will have a number of nodes -1 routes in between or edges in between. So that is what that many number of times we will process every edge, imagining that if we are processing it next time, that means the neighbor or source, in case of u and v, you might have got the updated cost by now. And processing means what? Processing is very straightforward, that in this loop now we are saying that for let me just format it. So there is a loop inside this, that for u comma v and w, so this is one edge. For every edge in my edges, so every edge is having three things: a source, destination, right? And by source and destination means in an edge that you have two nodes, so u node and v node, and what is the weight on that edge. What we are going to do for this is, if my distance is not infinity, that will check, means if you have not processed the source itself yet, then no need to do anything. So if in my distance array, if u is still infinity, then don't do anything. By that means if u is not infinity, which we define in our variable. And next thing is, if my distance for u, let me expand the size of this box for better readability. Okay, if I will add this weight, this w in this distance, and you can say that this distance is actually better than whatever v is already having, right? So what I'm trying to do is, if there is an edge from a to c, right, and whatever is the cost of c, so by default this is infinite for sure. If cost of c is going to be better, if I check whatever is the cost till a from the source and adding this cost of the edge, if this is a better cost, I will simply update the cost of v. This is pretty straightforward. This we just need to do how many times? this we need to do n minus 1, means v minus 1 times, where v is number of vertices. If this is the case, then I will simply do distance of v vertex is going to be distance of u plus w. That's it. So as straightforward as this. If you are done with this, that means ultimately you can return from this array. We will simply return distance of distance array. In this distance array, you will have whatever is the minimum cost to reach to every vertex from source. And we are done. Though there is one piece pending here, but overall this is the main algorithm which we are having. Now let's just establish the one more part which is I'm saying is pending, is in case there is a negative cycle. By that we mean that if let's suppose in this particular graph, if I'm having say from D to E, again you can go in minus 30, right? If I'm just defining this one more edge here, then what will happen, that you will be able to go again and again. Okay, let me do it here. So if I'm defining this new edge with minus 30 weight over it, so I will be able to go in this cycle and the cost will keep on reducing, because there is a cycle now. For this cycle we can never find an answer, right? But that case we have to write in our code, that if this is the case, I should be able to say, hey, I cannot find the answer. So that is one, you can say, call it an exception or something, which we will do separately. So let's call it like, I am calling it step 2. Let me increase the size to 48. Now what I'm going to do here is, for every edge now, I'll simply run the same loop, that for u, comma v, comma w in edges, if my distance of u is still not infinity, because there are possible that some of the edges were some of the vertices are like outside the main graph, there is a separate component. If that is the case, that means I cannot reach to that particular source, reach to that particular node from the given source. In that case, we will always have infinity for that particular node. Hence we need to put a check if this is not infinity. But I am saying, even after running the entire algorithm, which we did in step 1, still there is a case where let me just copy paste the same thing. If still there is a case that I can still better reaching to v from u, though we should have processed it already in the step 1, right? So this is the case where we are saying the cycle is a negative cycle is there. Okay, so we have kind of found out that there is a negative cycle. In this case, we will return whatever is, you can say -1 or say none or an empty array. That we cannot solve it because there is a negative cycle. This is an extra step, which is, you can say, copy paste of this step 1 inner loop and just return throw an error or return whatever you want to return in a negative cycle case. So this, as simple as this, code is very easy, but having the understanding of it is it only comes when you do comparative practice, that BFS versus then Dijkstra versus then Bellman-Ford, where you will be able to apply it. Now let's apply it in the question which we picked here. So there is a question on Bellman-Ford directly on Geeks for Geeks. This is where we will do the test first of our algorithm before we solve question based on it, where directly it is not asked, right? But in this one, this is directly talking about applying Bellman-Ford itself in case of a negative cycle, which we just saw what that case can be. In that case, we just need to return -1 as an array. So I'll copy paste the code which we wrote. Bellman-Ford define. Yeah, so this is, yeah, I'll call it like Bellman-Ford algo. I'll just say self so that I can call it easily. Okay. So here v is number of vertexes. This is actually same as what my code is expecting. In fact, yeah, I can in fact use this code directly, so I'll paste it here. Shift tab. Okay, indentation is fixed. In place of v, I'll call it n because that is what we are using in our code. I'll just try to compile it. There is still, okay, so this I can remove now. Let me compile it again. Compilation completed, and it is producing. Okay, so I'll just, oh, in this case I need to return -1. Oh, let me submit it. As per them, their infinity is something like this. Cool. Yeah, so it's working actually. So we got it that this is pretty straightforward. Let's do the time complexity. Time complexity, this code is actually pretty straightforward. We don't need to do too much in that. What we have here is, we have our first loop which is running v minus 1 number of times, where v is number of vertexes we are having, and inside that we are processing every edge. So this is straightforward, that v into e is the time complexity of this algorithm. There's nothing hidden here. This is pretty straightforward. We don't need to do anything else in this one. Yeah, cool. Now we'll try to solve some question based on it where it is not asked directly. So we'll find out a question and solve it.